So, we will discuss few problems. The first problem is so that the vibrational entropy of a 3D solid described by the Einstein model S equals to 3nk kb x by e to the x minus 1 minus ln 1 minus e to the minus x, where x equals to h nu by kBt. This is the problem. So that the vibrational entropy of a 3-dimensional solid described by the Einstein model is S equals to 3n kb x by e to the x minus 1 minus ln 1 minus e to the minus x, where x is h nu by kBt. So, to solve this problem, we have to use the expression for entropy. So, S is, we know S is kb ln q plus E average by T. So, E average is 3n ln q vibrational, and if we substitute this, so we get, or rather q here is q to the 3n, or we can write q is e to the minus beta h nu by 2 by 1 minus e to the minus beta h nu. That is small q or q vibrational here. So, this to the 3n. So, we write ln q is 3n minus 3n beta h nu by 2 minus 3n ln 1 minus e to the minus beta h nu. So, in order to get average of energy, we know how to calculate average of energy. So, this is del ln q by del b del beta when n and v constant. So, we have got value of ln q. If we now differentiate ln q with respect to beta at constant n and v, so we get del ln q by del beta at constant volume is minus 3n h nu by 2 minus 3n by 1 minus e to the minus beta h nu times minus e to the minus beta h nu times minus h nu. So, this is the value of del ln q by del beta. Okay. So, if we simplify further this one, we get average energy is 3n. So, average energy is minus of del ln q by del beta. So, we get average energy E is 3n h nu by 2 plus 3n h nu by e to the beta h nu minus 1. So, this is the value of average energy. So, now if we substitute all these things, we get entropy. So, S is now Kb ln q. So, Kb times minus 3 n beta h nu by 2 minus 3 n ln 1 minus e to the minus beta h nu plus 1 by t times 3 n h nu by 2 plus 3 n h nu by e to the beta h nu minus 1. So, this is the value of S. So, we get now beta is 1 by kBt, that we know. Okay, so, if we substitute that, we get S is minus 3 n h nu by 2t minus 3 n kb ln 1 minus e to the minus beta h nu plus 3 n h nu by 2t plus 3 n h nu by t times 1 by e to the beta h nu minus 1. So, this and this they get cancelled. So, we get S is 3 n kb x by e to the x minus 1 minus ln 1 minus e to the minus x. If we substitute as x is h nu by kBt. Okay, so, this is only very simple analytical problem. Okay, so, we can prove that the entropy of a 3-dimensional solid which follows Einstein model is 3 n kb x by e to the x minus 1 minus ln 1 minus e to the x, where x is h nu by kBt. So, okay, so the next problem we discuss now is very interesting problem. Consider a solid where a fixed number of atoms, n form into a crystal where the atoms sit in an ordered array on the sides of a lattice. Consider a solid where a fixed number of atoms n form into a crystal where the atoms sit in an ordered array on the sides of a lattice, and Schottky defect is a lattice without a lattice site without an atom. Assume that there are small n number of lattice sites that do not have any atom and each defect costs energy of epsilon. Calculate the Helmholtz free energy as a function of small n, that is A n. Also show that the equilibrium number of defects can be written as small n average is e to the n capital N by e to the beta epsilon minus 1. Okay. The second problem is, consider a solid where a fixed number of atoms n form into a crystal, where the atoms sit in an ordered array on the sides of a lattice, and Schottky defect is a lattice site without an atom. Assume that there are small n number of lattice sites that do not have any atom, and each defect consists costs energy of epsilon. Calculate the Helmholtz free energy as a function of small n, that is A in bracket n. Also show the equilibrium number of defects can be written as capital N equals to small n average equals to capital N by e to the beta epsilon minus 1. Now, from this problem it is clear that capital N number of sites in the lattice are occupied, and small n number of sites in the lattice are unoccupied. So, total number of lattice site is capital N plus small n, right. So, what is the weight of the distribution? Okay. So, weight of the distribution if we call weight of the distribution is W. So, weight of the distribution is capital N plus small n factorial by capital N factorial and small n factorial. So, we get ln W is ln n plus n factorial minus ln n factorial minus ln n factorial, or you can write ln W is n plus n ln n plus n plus n plus n minus n ln n minus n, and then minus n ln n minus n. So, we get ln W is n plus n ln n plus n minus n ln n minus n ln. So, this is the value of ln W. So, S entropy S is related to ln W by the expression Kb. S is ln S equals to Kb ln W. So, if we substitute the value of ln W here in the expression of S, we get S is Kb so S is Kb at n plus n ln n plus n minus n ln n minus n ln n. So, this is the value of S, and A, which is function of n, is E minus Ts. So, what is E? E is E average is n times epsilon, because we have n small n number of sites are vacant and each defect costs energy of epsilon. Okay, so, we get a n is n epsilon minus kbt n plus n So, this is the expression for Helmholtz free energy. So, Helmholtz free energy A, which is function of n, is n times epsilon minus kbt n plus capital N plus small n times ln n plus n minus n ln capital N ln capital N minus n small n ln small n. So, this is the expression for Helmholtz free energy. So, we get equilibrium configuration from this Helmholtz free energy by minimization of. So, the minimization of ANT, the minimization of ANT AN with respect to small n gives the equilibrium number of defects. So, we need to maximize, we need to differentiate a n with respect to n and then make it 0. Okay. So, if we do it, so first we differentiate a with respect to n, we get epsilon minus okay. So, first we simplify a, then it will be much easier. So, if we simplify a n first and then if we do the differentiation, it will be much easier. So, a n is n epsilon minus kbt n kbt ln n plus n minus n kbt ln n plus n minus n ln n minus n ln n. Now, if we differentiate a with respect to n, we get epsilon, first n epsilon gives epsilon and then we have n by n kbt by n plus n minus n kbt by n plus n minus kbt ln n plus n minus 0 minus ln n minus n times 1 by n. So, we get dAn by dN. So, we get dAn by dN equals to epsilon minus kBt times ln n plus n plus 1 minus ln n minus 1, and this gives 0 as we said. So, we get epsilon minus kBt ln n plus n by small n equals to 0. So, it gives us n is n by e to the beta epsilon minus 1. So, we can prove that small n equals to capital N by e to the beta epsilon minus 1, where beta again 1 by kBt. Okay. So, next problem we discuss says problem number 3. A two-level system of n is nothing but n1 plus n2 number of particles is distributed between two states 1 and 2 with energies U1 and E2 respectively. The system is in contact with a reservoir at temperature T Kelvin. If a single quantum emission occurs, population changes n2 minus 1 and n1 to n1 plus 1. For n1 much greater than 1 and n2 much greater than 1, obtain the entropy change of the system second problem, the entropy change of the reservoir and problem C is from A and B obtain or derive the Boltzmann distribution. Derive the Boltzmann relation. So, this problem states a two-level system of total n number of particles, where a capital N is the total number of particles equals to n1 plus n2, distributed between two states 1 and 2 with energies E1 and E2. So, number of particles in energy E1 is n1 and number of particles in energy level E2 is n2 at the beginning. The system is in contact with a reservoir at temperature T Kelvin. If a single quantum emission occurs, the population changes n2 to n2 minus 1 and n1 to n1 plus 1. For both n1 and n2 much greater than 1 obtain the entropy change of the system or for the process, the entropy change of the reservoir, and from the answers of A and B, we need to derive the Boltzmann relation. So, before emission, the number of particles in energy state U1 was N1 and the number of particles in energy state E2 is N2. After emission, the number of particles in energy state U1 is N1 plus 1 and the number of particles in energy state E2 is N2 minus 1. So, S before emission the weight of the distribution if we say the weight of the distribution is W1. So, W1 is we have total capital N number of particles and then we have N1 number of particles in energy level E2 E1 and N2 number of particles in energy level E2 and capital N is N1 plus N2 factorial by N1 factorial times N2 factorial. So, this is the weight of the distribution before emission. So, after emission, the weight of the distribution if we say the weight of the distribution is W2 after emission, then again we have total n number of particles, but now we have N1 plus 1 particle in the energy level E1 and N2 minus 1 particle in the energy level E2. So, we get N1 plus N2 factorial by N1 plus 1 factorial and times N2 minus 1 factorial. So, we have got the weights of the distribution before emission as well as after emission. So, once we got this weight of the distribution, we can calculate entropy before emission and entropy after emission. So, before emission the entropy before emission so we know the weight of the distribution related to entropy. So, if we say the entropy before emission is S1, so S1 is Kb times ln W1. So, we get S1 is Kb ln W1 is N1 plus N2 factorial by N1 factorial times N2 factorial. And if we simplify this one, we get S1 is Kb So, this is the value of entropy change before emission. So, the entropy change before emission is, we say S1 is Kb N1 ln N1 plus N2 by N1 plus N2 plus ln N1 plus N2 by N2. So, the entropy change after emission is the entropy after emission, if we say the entropy is S2 is Kb ln W2. So, we will substitute the value of W2 here. So, we get S2 is Kb, W2 is N1 plus N2 factorial by N1 plus 1 factorial times N2 minus 1 factorial. So, we get S2 is Kb ln N1 plus N2 factorial minus ln N1 plus 1 factorial minus ln N2 minus 1 factorial. Now, if we apply Stirling's approximations, because both N1 and N2 are very, very large. So, we write Kb, S2 is Kb times N1 plus N2 minus N1 plus N2, then minus this is the first term and now the second term. And then we have one more term here, so that is your so if we simplify, we get S2 is Kb N1 plus N2 ln N1 plus N2 minus N1 plus 1 ln N1 plus 1 minus N2 minus 1 ln N2 minus 1. So, change in entropy of the system. So, the entropy change of the system due to this process, entropy change of the system, if we say delta S is S2 minus S1. So, if we do it, we get S delta S is Kb ln N2 by N1 plus 1, or you can write delta S nothing but Kb ln N2 by N1, because as N1 is very, very large. So, N1 plus 1 we can write as N1. So, this is the entropy change of the system and entropy change of the reservoir. We said delta S is E1 minus E2 by T, right. Okay. So, the or E2 minus E1, not E1 minus, but rather E2 minus E1 by T. Okay. So, we get, since so the entropy change of the system, if we say delta S1 here, and the entropy change of the reservoir if we say delta S2. So, delta S1 is nothing but equals to minus of delta S2. So, if we substitute, we get Kb ln N2 by N1 equals to U1 minus E2 by T. So, we get N2 by N1 equals to e to the minus beta E2 minus E1. So, this is nothing but Boltzmann relation. Okay, so, we discuss another problem here. So, the third law, the problem number 4 is, yes, 4 is the third law of thermodynamics asserts that limit t goes to 0 is equals to 0 for any macroscopic system. What condition has to be satisfied for this claim to hold. Okay, so the problem number 4 says the third law of thermodynamics asserts that limit s goes to 0, limit t goes to when limit t goes to 0, s goes to 0 for any macroscopic system. So, what condition does or what condition has to be satisfied for this claim to hold? Okay. So, we know partition function q is sum over I sigma I e to the minus beta e I, where sigma I is the degeneracy of ith level. Okay. So, we get, if we expand it, we get sigma 0 e to the minus beta e 0 plus omega 1 e to the minus beta e 1 plus omega 2 e to the minus beta e 2, etc., where 0, omega 1, omega 2, etc., are the degeneracies of the ground state, first excited state, and second excited state, etc. And E0 is the ground state energy, U1 is the first excited state energy, E2 is the second excited state energy. So, here omega 0 is the degeneracy of ground state, omega 1 is the degeneracy of first excited state, omega 2 is the degeneracy of second excited state, and so on, and so on. Similarly, E0 is the energy of the ground state, E1 is the energy of the first excited state, E2 is the energy of the second excited state, and so on. And so on. Okay, now, what we do, we further simplify Q by taking out sigma omega 0 e to the minus beta e 0. If we do it, we get 1 by 1 plus omega 1 by omega naught e to the minus beta delta e 1 plus omega 2 by omega naught e to the minus delta beta delta e 2 to the minus beta delta e 2, and so on, where delta e 1 is e 1 minus e naught. Okay. Delta e 2 is e 2 minus e naught, and so on, and so on. Okay. Now, at low temperature, or when T goes to 0, beta goes to infinity. So, delta beta delta U1 is much greater than 1, and so on. So, we get Q is omega 0 e to the minus beta e 0. Okay. And so, if you take log, we get ln Q is ln omega 0 minus beta e 0. Okay. Or you can write Kb ln Q is Kb ln omega 0 minus E 0 by T. We can write S is nothing but Kb ln omega 0. So, this says S goes to 0 when omega 0 goes to 1. That means, in order to hold that claim, the ground state must be degenerate, non-degenerate, must be non-degenerate to get limit t goes to 0, s goes to 0. So, it says that ground state must be non-degenerate, or the degeneracy of the ground state must be equal to 1 in order to get, or in order to hold the relation limit t goes to 0, s equals to 0. Thank you.